Imagine every encrypted message on Earth cracked open in seconds, every bank account, every military secret, every private conversation exposed. Now imagine a single drug discovery that once took 15 years, completed in weeks. This is not science fiction. Billions of dollars are being poured into making it real, and a battle is unfolding between nations and corporations, unlike anything since the space race. Who will harness quantum mechanics first, and what will it mean for the rest of us? The answer depends on solving a problem so fundamental, most experts are not sure it can be solved at all. Quantum computers operate in a world where the rules of ordinary logic no longer apply. Imagine flipping a coin. In the classical world, it lands as either heads or tails. But in the quantum world, a qubit, short for quantum bit, is like a coin spinning in midair, existing as both heads and tails at once until someone looks. This is superposition, the first key to quantum power. Instead of choosing between 0 and 1, a qubit can blend them, holding probabilities for both. This is what lets quantum computers explore many possibilities at once, far beyond what any classical computer can manage. But quantum strangeness does not stop there. Picture an orchestra, every instrument tuned so precisely that a change in one echoes instantly across the group. Entanglement links qubits so tightly that their fates become intertwined, no matter how far apart they are. Change one, and the other responds instantly. Einstein called this spooky action at a distance. In quantum computing, entanglement is the secret sauce that allows information to be shared and processed in ways that defy everyday experience. To visualize a qubit state, physicists use something called the Bloch sphere. Instead of a flat switch between 0 and 1, a qubit state can point anywhere on the surface of a sphere, capturing every possible combination of superposition and phase. This sphere captures the full richness of quantum behavior in a single, elegant picture. Think of the Bloch sphere as a map for every possible qubit state. As John Preskill, the physicist who coined the term quantum supremacy, once put it, these machines harness the weirdness of quantum mechanics itself, not just faster chips or better code. The promise is extraordinary, but so is the difficulty. Qubits are delicate. Even the faintest whisper from the outside world can collapse their fragile state, erasing the quantum advantage in an instant. That is why the hum of dilution refrigerators, the silence of shielded labs, and the careful choreography of quantum gates are all part of the race. The stage is set. The next challenge is building machines that can keep this quantum magic alive long enough to do something useful. Inside every quantum lab, the hum of the dilution refrigerator is more than background noise. It is a countdown. Qubits, whether they are trapped ions, superconducting loops, or flickers of light, can hold their quantum secrets for only microseconds to, at best, a few seconds. For most superconducting systems, the window lasts just 70 to 120 microseconds before quantum information dissolves into ordinary noise. Trapped ions stretch this to a few seconds, but the principle is the same. The clock is always ticking. Decoherence is the enemy. Any stray vibration, a single photon, or a hint of magnetic interference can collapse a qubit's delicate state. To keep quantum information alive, researchers bundle thousands of physical qubits together, hoping to build a single logical qubit that is robust enough for real computation. The numbers are staggering. Current error correction schemes demand around 1,000 physical qubits for just one logical qubit. IBM's experiments with the surface code, for example, used 81 physical qubits to encode a single logical qubit. But even then, the logical error rate hovered around 2 in 1,000. This overhead is why full-scale quantum computers remain out of reach. As John Preskill once said, the promise is extraordinary, but so is the difficulty. In the NISQ era, noisy intermediate scale quantum, machines with dozens or even hundreds of qubits cannot yet run the algorithms needed to break cryptography or revolutionize chemistry. But they are not powerless. Early wins come in narrow pockets, simulating small molecules, optimizing logistics routes, or tackling complex scheduling problems. In these niches, quantum hardware can sometimes outperform classical supercomputers, especially when paired with clever error mitigation techniques. Yet every demonstration comes with a caveat. The same noise that limits what quantum computers can do also makes their results hard to trust. Each experiment is a balancing act, pushing the boundaries of what is possible while wrestling with the stubborn reality of error rates and fleeting coherence. The race is on, not just to add more qubits, but to build machines that can keep their quantum magic alive long enough to matter. The next moves belong to the companies and countries willing to bet billions on cracking these barriers. Inside the largest tech companies, quantum computing is a contest of scale, vision, and technical faith. IBM pushes hardware to its limits, unveiling Osprey, a 433-qubit processor, in 2023. The machine's superconducting circuits, cooled to near absolute zero, are the centerpiece of a public roadmap. Osprey now, Condor, with over 1,000 qubits next, and Starling, a prototype fault-tolerant system, by 2026. Each milestone is measured by quantum volume and outside verification. For Dario Gil, IBM's quantum chief, the mission is clear. We're not just building chips, we're building the backbone of a new industry. Google's approach is bold, defined by headline moments and relentless engineering. In 2019, its Sycamore chip ran a random circuit faster than any supercomputer, a feat Sundar Pichai likened to the Wright brothers' first flight. Since then, the focus has shifted to refining gate fidelity and error rates. The next leap, the Bristol chip, is rumored to break the 1,000-qubit mark, but Google guards its progress, releasing few details as the world watches and debates every claim. Microsoft bets on a different physics. Rather than scaling up noisy qubits, its researchers chase the topological qubit, encoded in the braiding of quasi-particles. In 2024, Microsoft demonstrated controlled braiding, a lab-scale achievement that hints at error correction woven into the qubit itself. Azure Quantum offers access to various hardware, but the real ambition is to leapfrog today's error correction limits. Amazon sidesteps the hardware race, focusing on cloud access. Amazon Web Services. Bracket, launched in 2022, connects users to quantum devices from IonQ, Rigetti, and Amazon's own photonic prototypes. In 2025, Amazon integrated Bracket with high-performance computing systems, blending quantum and classical computing. Each company's path reveals a distinct vision of what it means to win the quantum race. Venture-backed quantum startups operate under a different kind of pressure. Each breakthrough is a wager, every delay a threat to survival. Rigetti Computing, spun out by Chad Rigetti after his stint at IBM, made headlines in 2022 with a $300 million SPAC deal. Their superconducting qubits, built on the Aspen chip line, once promised quantum advantage. By 2024, the company shifted gears, focusing on hybrid cloud services to keep investors engaged. Chad Rigetti reflected, "We overpromised on logical qubit depth. Now it's about delivering reliability." IonQ, founded by Chris Monroe and Jungsung Kim, took a different route. Their 2021 public listing brought in $200 million, fueling their push into trapped ion technology, ytterbium ions suspended by lasers, offering all-to-all connectivity and high gate fidelity. IonQ's hardware now powers quantum services for Amazon and Microsoft, a first for any startup in the sector. Their team claims, "We can run longer, deeper circuits before noise sets in." PsiQuantum, the photonics contender, raised $1 billion in 2024, backed by sovereign wealth funds. Their approach swaps cryogenics for silicon photonic chips, sending billions of photons through waveguides. PsiQuantum's founders, veterans of optical networking, aim for a million-qubit machine by 2030, but their roadmap depends on global semiconductor partners and strict investor covenants. Toronto's Xanadu, with $650 million raised, also bets on photonics. Their Borealis chip, a 128-qubit Gaussian boson sampler, launched in cloud beta with Microsoft Azure in 2025. Xanadu's open-source Penny Lane toolkit draws in developers, while CEO Christian Wiedbrook insists, "We are building quantum for the cloud, not the cleanroom." D-Wave, the outlier, went public in 2021 and reached profitability by 2023. Their quantum annealers, designed for optimization, have found paying customers. CFO Laura Ransom declared, "We are not just burning cash, we are delivering value now." Jiuzhang 4.0, the latest photonic processor from the University of Science and Technology of China, shattered previous records by detecting up to 3,050 photons in a single run. In the language of quantum hardware, this is less like flipping a coin and more like orchestrating a blizzard of light. Each photon a note, every detection a fleeting moment of quantum harmony. The experiment, published with raw data for independent scrutiny, claims a computational feat beyond the reach of classical supercomputers. Follow-up efforts in the West have yet to close the gap, leaving the Jiuzhang team's claim of quantum advantage standing, at least for now. This is not just a laboratory milestone. It's a signal flare in a global contest where state budgets rival those of entire industries. China's national quantum program, with its photonic breakthroughs and plans for superconducting prototypes, is only one front. The United States, under the National Quantum Initiative Act, has committed $9 billion through 2026, funding a web of research centers, testbeds, and military-linked labs. Congressional hearings frame quantum as a dual-use technology, vital for both economic leadership and defense, with explicit calls for quantum-secure communications and next-generation sensing. Europe's quantum flagship, launched in 2021, brings together 27 countries with a 10 billion euros commitment over a decade. The goals are a quantum-ready continent by 2030, a secure communication backbone, and a new class of quantum sensors. Japan's quantum innovation strategy earmarks 150 billion yen, channeling resources into hardware, quantum networks, and security pilots from Tokyo to KEK. Canada, with $1.2 billion in public funding, focuses on research hubs like Waterloo and McGill, linking quantum science to defense and industry. Across continents, these investments are not just about research, they are about positioning. Policy documents and budget reports invoke the urgency of quantum for national security, economic competitiveness, and scientific prestige. Each new demonstration, like Jiuzhang's photonic cascade, becomes a benchmark for capability and a lever in diplomatic and military strategy. The global quantum race is no longer theoretical. It is measured in billions, in photons, and in the urgency of those who see the next breakthrough as a matter of national interest. Crypto at risk. The promise of quantum computing glimmers with possibility, but beneath that promise runs a current of unease. At the heart of modern digital life, banking, medical records, and classified government files lie a cryptographic shield built on mathematical problems no classical computer can break in reasonable time. RSA and elliptic curve cryptography, the bedrock of secure communication, depend on this gap. But quantum algorithms threaten to close it. In 1994, mathematician Peter Shor described an algorithm that, on a fault-tolerant quantum computer, could factor large numbers exponentially faster than any known classical method. Shor's algorithm, once a theoretical curiosity, now sits at the center of global cybersecurity strategy. The threat is not abstract. With enough logical qubits, estimates range from 4,000 to 10,000. Shor's algorithm could crack RSA 2048, the standard for online security, in days or even hours. Elliptic curve systems, prized for their efficiency, are equally vulnerable. The only buffer is time. Today's quantum machines are noisy, and error correction remains a monumental challenge. But the clock is ticking. Recognizing this, the U.S. National Institute of Standards and Technology, NIST, launched a global competition to standardize quantum-resistant algorithms. After years of cryptanalysis and public scrutiny, 4 lattice-based schemes, Crystal's Kyber for key exchange, Crystal's dilithium and Falcon for digital signatures, and the hash-based Picnic, have reached the final round. Draft standards from NIST are expected in early 2026, with official publication targeted for the end of that year. Federal systems will be required to migrate soon after, and guidance for the private sector will follow within 12 to 18 months. The urgency is not just technical, but practical. Enterprises face a multi-year migration, cataloging every system that relies on RSA or elliptic curve cryptography, testing hybrid deployments, upgrading key management, and replacing certificates across sprawling infrastructures. CISA and NIST both warn that migration should begin now, not after standards are finalized. The danger is not only in future attacks, but in data being harvested today, encrypted and stored for decryption once quantum machines mature. The risk is real, and the window for preparation is narrowing. As quantum hardware inches closer to the critical threshold, the migration to post-quantum cryptography is no longer a theoretical exercise. It is a race against time, one that will define the security of the digital world for decades to come. A new kind of accessibility is reshaping the quantum landscape, one that does not require a multi-million-dollar lab or a PhD in physics. Cloud quantum platforms, IBM Quantum Experience, Amazon Web Services Briquette, and Microsoft Azure Quantum have opened their doors to anyone with curiosity and a laptop. With pay-as-you-go pricing, a student in Nairobi can run the same quantum circuits as a hedge fund analyst in New York. Subscription models start at just a few dollars per hour, a far cry from the days when quantum hardware was locked behind institutional walls. Software development kits like Qiskit, Cirq, and Penny Lane have become the entry points for a new generation of quantum developers. Qiskit, launched by IBM, now counts over 350,000 registered users, with open-source tutorials that walk beginners from their first qubit to advanced error mitigation. Cirq, Google's contribution, is tailored for circuit design and integration with classical workflows. Penny Lane, built by Xanadu, bridges quantum hardware and machine learning, letting developers write hybrid algorithms that run across superconducting, trapped ion, and photonic systems, all from a single interface. Yet as access widens, a bottleneck tightens. The demand for quantum-savvy engineers and researchers far outstrips supply. In a 2025 industry survey, 70% of hiring managers reported unfilled quantum software positions, and more than half face shortages in hardware-focused talent. Universities are scrambling to keep up, launching joint computer science and physics programs, but the pipeline remains thin. Companies like Rigetti and Xanadu have responded by sponsoring training boot camps and accelerator programs, hoping to cultivate the next wave of quantum specialists. The result is a paradox. The tools for quantum exploration are more available than ever, but the expertise to wield them is scarce. As cloud platforms lower the barrier to entry, the race is increasingly fought not just in hardware labs, but in code repositories, online forums, and virtual classrooms around the world. Winners, losers, unknowns. The endgame for quantum computing is anything but settled. 4 futures stand before us, each shaped by the choices of engineers, policymakers, and the unpredictable physics of qubits themselves. In one scenario, a single platform, perhaps superconducting circuits or silicon photonics, pulls ahead and consolidates the market the way CMOS did for classical chips. If this happens, the winner could lock in hardware standards, drive costs down through mass production, and dominate the cloud platforms that serve quantum power to the world. Export controls would tighten, with governments treating quantum chips as strategic assets, much like advanced semiconductors today. The result is a handful of companies and countries setting the rules, and everyone else adapts or falls behind. A second possibility is fragmentation. Competing architectures, trapped ions, photonics, and annulars each find their niche. Superconducting qubits excel at machine learning, trapped ions at chemistry, photonics at secure communication. No single player owns the field. Instead, the market resembles today's cloud ecosystem, with customers choosing the right tool for each job, and no one platform able to dictate terms. Security risks are spread out, but so are the rewards. National programs and export controls remain in play, but technical diversity blunts the impact of any one breakthrough. A third outcome is commoditization. Hardware matures to the point where quantum chips become interchangeable parts, much like memory modules or graphics cards. Manufacturing shifts to the lowest cost producers, and the real value moves to software, algorithms, and integration with classical systems. Startups and open source communities thrive, but margins shrink. National champions may lose ground to global supply chains, and the quantum advantage becomes accessible to all, at least in theory. Then there is the unknown. A classified leap, a black swan event, or a physics discovery could rewrite the rules. A government or consortium could cross the threshold in secret, upending markets and security overnight. Or the technical hurdles could prove steeper than expected, and the world could settle into a prolonged NISQ era, useful for some, but never the revolution once promised. Each scenario carries different winners and losers. Market leaders today could be overtaken tomorrow. Policies written for one outcome may backfire in another. The only certainty is that the quantum race is not just about machines. It is about who shapes the rules of the next era of computing and who gets left behind. The world's most powerful computers are still locked in a race, their qubits balanced on the edge of possibility and risk. As nations and corporations invest billions, the outcome will redraw lines of trust, security, and discovery in real time. The question now isn't who will win, but how we'll choose to use what's unlocked. The next move belongs to all of us. Share your thoughts below.